Hello everybody, this is Cameron Snow with Danomics.com. In this video, I'm going to be diving into pore pressure and how we can make some of those calculations in Danomics. And we're going to be having a bit of a blend of actual hands-on setting of parameters and theoretical discussion on some of the things you should expect to see within your data when you are doing this interpretation. So let's get started. First thing, where should you be in your analysis by this point? Well, you should have already done your log QC work, done things like normalize your data if needed, do bad hole repair. You would have already calculated your reservoir properties. And now we'll move on to some of the advanced interpretation here that you'd have access to in Danomics, including the pore pressure calculation. So we are going to jump to the pore pressure module. And what we'll see is that we have a few different options here. And I'm going to zoom out a little bit so we can see the entire well log from essentially surface down to TD. And let's take a look at what some of the options are here. So we have things like our hydrostatic pressure gradient and our lithostatic pressure gradient. Now, if we had, let's say some MDT or RFT data to let us understand our pressures, we could bring that data in as a points data set and display that on the track to help us calibrate our hydrostatic. Same as if we had like some leak-off test or fracture injection test. Once again, we could bring that in and display that data and use that to help calibrate our lithostatic pressure gradient. We don't have that in this case, so we're just going to use our knowledge of some of the local gradients here to set those. And with respect to the pore pressure, the methods that we have to calculate that are we have the Eaton methods for sonic and resistivity, both the standard Eatons and the modified Eaton approaches. The modified Eaton approaches, these are the ones that allow us to look at a normal compaction trend line within our data, whereas the standard methodologies just use a single value there. So we're going to explore both of those. Now, Eaton's methodologies were specifically designed to look at the pressure within the shales. So you may notice over here, we have some highlighting here in our section. That is showing us where we have shales flagged, and that's the only areas where we are doing our pressure calculations. Now what is flagged here, we can set using a V-clay cutoff. So in this case, maybe we want to change that to, let's say, I don't know, a 30% clay volume cutoff. So we can see it highlights, the sections we have here where we have these gray shells. It also highlights some shells down here in the base. All right, so we'll assume that is okay for now. Now let's go into how we want to set some of these parameters. So in general, when we're using the standard methodologies, and I'm going to zoom in here to some of the shells that are in our primary section, they're in between some of our main targets. What we want to do is we essentially want to put our trend line through the data. We'll start here with the resistivity. And remember, we're setting it right now just for the basic Eaton method, not the modified Eaton. And quite simple, all you do is look at the value here in the shell, and we will adjust that. And we'll start off with resistivity. We have read our resistivity to be about 4 ohms. And what we look at here is it's updated this red line. This is the pore pressure using the Eaton method. And we see that we are hovering right around a normal pressure gradient for some of this. Some areas we are below, some areas we are above. And in general, what we would look for in the resistivity, what we would expect to see is we'd expect to see resistivity increasing with depth. And then as we enter an overpressured zone, that resistivity curve would would kind of turn over and start to come back toward lower values. Um, this has to do with our understanding of the cation exchange capacity within shells. That's what drives that trend. But know that in general, in normally pressured systems, that resistivity will in general increase with depth and then uh, start to reverse um, as you get into an overpressured regime. Now, when we are setting our sonic, for our standard Eaton, what we can do is same thing. We'll come in here to our shells. We'll read off a value. Here I can see that it's about uh, 82 microseconds per foot. Um, and we can update that value. This will update the curves. And what we see now is once again, we are on a normal trend through our shallow intervals into these shells. And in most cases, we are right along hydrostatic, which is what we'd expect considering, for a lot of this area, we don't expect to see significant overpressure in these shells. Um, Now, what we'll notice is if we zoom out, we're good here through this part of the data, but we're kind of off for this shallow area here. So can we address that a little bit better? So this is where we had used the modified Eaton formulations. And what we'll look at here is, how we can set this up. So with our sonic here, we can come in and what we need to set are two parameters. This is our DTO and our B exponent for our normal compaction trend line. You'll have to play around with these a little bit to get the right numbers, but in general, the curvature of this line is controlled by this B exponent, and our left to right shift on it is a product of the DTO, and we can play around with these values a little bit. And what we can see is that as we update that, now we can really start to match the sonic value in our shells here, and this gives us a nice normal compaction trend line that we can use to calculate potential overpressure. So we see that the sonic is behaving as expected in this interval. Now, the resistivity is actually behaving a bit opposite of what we would expect. So we have to make sure not to fall into a trap here, because we could fall into a trap of using a compaction trend line that is actually reversed of our expectations, and that's not what we want to do here. Um, what we'd want to do is we would want to come in and set a compaction trend line that meets our expectations here. Perhaps we need to try to understand what's driving some of these calculations. We want to look at where we have overpressure, and what we want to do is we want to get these two methods to really sync up, so we've kind of tied the loop there. Now, up here in the shallow part of this section, we have some coal bed methanes up here. I think those are throwing off our resistivity measurements in this interval, and that's why we're getting a poor fit to our method here, but why our sonic is holding in. The other thing to note about these methods is if we have an organic shell formation, so like our Niobrara, one of the things that you'll notice is that our resistivity behaves quite poorly in this area. And this is because organic shells have excess resistivity, so you're always going to get a poor calculation using the resistivity methods in your organic shells. So that's one thing to keep in mind. Now, a few other options that we get to set here in Danomics. So first of all, we need to decide, and this is maybe a bit aesthetic. do we want to allow under pressure in our calculations? I'm not really worried about under pressure in any of this area, so I am going to uncheck the allow under pressure. And now what we'll see is that goes away, and that clips our calculation. We may also want to say, hey, do we want to calculate it over all of the interval? Do we want to fill the missing values with hydrostatic? I'm going to say, hey, let's fill those with hydrostatic in here. Now we get that continuous pressure profile. And once again, we would want to calibrate this. We'd want to go through and we'd want to overlay some of our mud weight information on this to help build up a richer display that we can use. And then we'd want to go through and say, hey, does this make sense? Do we have overpressures down here in some of these deeper formations? Do we see drilling problems down here? And in fact, in the muddy, we often see significant drilling problems. And so that would indicate that, yes, we actually do have potentially some overpressures down here that we need to think about. All right, so I hope that was useful. If you are following along in this series, I would encourage you to do a little bit of work here, because we're going to build on this in our next video when we start looking at wellbore stability. All right, I hope this was interesting. If you'd like to learn more, feel free to contact us at sales@danomics.com. Thank you.